So we're all delighted that you've come to hear what ARPA-E finds exciting right now in new energy. I'm Howard Branz. I'm a program director at ARPA-E, and I'm joined by four of my colleagues here. And what we talk about today will be conditioned by our experience at ARPA-E. Some of us have been around a long time, others are rather newcomers. I'll be talking about some projects that are really coming to fruition now, that are becoming technologies, not just ideas. Ping Lu, program director, will be talking about a program that he recently funded, so there's no real results yet, but I'll tell you where we have just made some investments. Jonathan Burbaum, another program director, will talk to you about a program that's being judged right now. The proposals are in, and we'll see which good ideas he decides to fund. Mike Kane, who's a fellow at ARPA-E, will tell you about a program, or a class of programs actually, that he really thinks is very promising for ARPA-E. And Schiff will tell you about a program that he's considering getting started at ARPA-E. So you'll get the full range of what we do. So I guess I'm up first, and we're going to go in that order. So, this is a reminder first that where you have about half the time allocated to our quick pitches. We're on very strict time limit, so there definitely will be time left for questions, about 30 minutes worth. You can text or tweet your questions to us. They'll come through this iPad over here. Hopefully, I'll be able to interpret them right and pass them on to the others. So please, at the end of each presentation, formulate your questions and send them in while it's still fresh in your mind. So I appreciate that. And yeah. So think about where you sit right now. There are photons zipping around this room, each one carrying energy. Those photons, back a slide, please. Those photons are attached to light waves of different colors and frequencies. Thank you. And these photons are all around us. And the idea of detecting, harvesting, converting them is an enabling technology for energy on the planet, because nearly all the external energy that comes to Earth comes in the form of photons, and much of the heat transfer is mediated by photons on Earth. I've been at ARPA-E now for nearly 3 years, and I've seen a lot of brilliant ideas come in that have to do with optics. And what I want to do is tell you about 5 of them today that are really technologies, and we hope moving to the market. Thanks. Next slide. So when you have a window, it's normally clear, and that means visible and ultraviolet come in, and so does the heat-bearing near-infrared that you can't see. Click. Is there a clicker up here? No. Okay. Yes. So conventional electrochromics have been around for nearly 50 years, and they block all that visible and near-infrared light with a small electric field applied, so that you can have control of the daylighting, whether there's glare, you can use daylighting, and also what the solar heat gain is. Now, our team from Texas and a small company, Heliotrope, that they've started, is developing a new kind of electrochromic window that uses plasmonics to independently switch those two kinds of light coming in through the window. So they're able to block the near-infrared photons in a third mode while still letting visible light in to reduce daylighting mode. One of the exciting things is that this window should be entirely solution processed for low cost. Now, this Cheryl introduced this morning, so I won't go into it deeply, but with nanophotonics, you can actually make this astonishing cooler. You put it up on the roof, as is shown on the right, and it emits radiation into deep space at the same time as it's brilliantly white. So it's deeply black in the thermal infrared photon regime, and bright white, reflective for sunlight. As a result, it cools by 8 degrees Fahrenheit spontaneously with no power applied. Here's a technology that's all about detecting the photons that are coming at us when we walk around a building. Now, The challenge of energy audits today is they're just too expensive. You send a highly skilled engineer with a pad of paper or maybe an iPad and an infrared camera, and he or she takes notes on what they're seeing and when they took the pictures, and then tries to assemble it. And to do a 20, 30-story building takes days. They're developing a backpack that you just can have a relatively unskilled person walk through the building, turn in each room, and come out, and you get both optical images from the 3 optical cameras mounted on the backpack and infrared images from the infrared cameras mounted, and then distances to the walls from LiDAR to overcome the fundamental problem of indoor mapping. The fundamental problem of indoor mapping is that there's no GPS inside buildings. When they're done, they can make a 3D map that you can joystick through. Now the engineer can joystick through it. The computer will flag thermal anomalies, and energy audit time will be reduced by a factor of about 10, and we think the cost will go down by a factor of 3 to 5. And there's a new startup formed around that, too, called Indoor Reality. It's a Berkeley technology. Now, one of the problems with solar energy is that the sun disappears at night. Photons just stop coming to us. As a result, while PV is great for daytime electricity, this group and a number of others funded through our FOCUS program, this is the GTI and UCal group, is trying to develop a new kind of solar receiver that goes in a parabolic trough that gets electricity from solar cells and high temperature, high grade, high value heat that's stored for dispatchability later on. So you can store the heat, go through a heat engine, and generate energy afterwards. At the focus of that parabola is a very unconventional receiver, light from the primary parabolic reflectors coming in there. The PV cell then makes electricity from the visible photons while reflecting all the subgap photons, all the invisible near-infrared photons, to a central location where you heat this fluid, a new kind of thermal fluid that's able to go up to high temperature. Finally, I want to show you technology from Sunfolding, a small company out of Other Lab, and they are trying to take all the costs of mechanical tracking out of the system. At half the cost of mechanical tracking, you can extend the solar day by a couple of hours. And you can follow the sun as it transits through the sky, which is one of the big problems for all kinds of solar energy. Their first application is in photovoltaics. And you can see what they've got here is a blow-molded bellows. And those wires there are not bringing electricity in, as usually goes to the motors in mechanical trackers, but bringing in compressed air that can turn the solar panel, as I showed. The total cost reduction of photovoltaic energy should come to somewhere between 2 and 4 cents a kilowatt hour today. As most of you know, you pay about 10 cents for your electricity today. Most photovoltaic systems are down around 11 or 12. So this could really be the difference for utility scale and commercial industrial scale solar energy. So in summary, in the solar and buildings markets, we think there's $1 trillion energy market. There's a lot of advanced science going on in photonics and plasmonics and other areas, and we welcome submissions to the Open FOA 2015.
So good afternoon. My name is Ping Liu. I'm a 30-year program director at ARPA-E. For many of you who know me in the audience, I'm a battery person, but that's not what I'm going to talk about today. I'm going to give you an overview of an exciting new program we're just launching. It's called a Delta. You will wonder, what is it? In one sentence, actually, we're trying to literally heat and cool people inside a building. That's really what it is. You wonder why we are interested in that. The problem we're trying to solve is really reduce the energy we consume to heat and cool buildings. So in the US right now, we consume about 13–14% of total energy use just to run air conditioning and heating. Equal amount of greenhouse gas emissions for this application. Part of this huge energy consumption is really to keep everybody, quote unquote, comfortable. So then you wonder, what's the standard of that? In order to, over the course of decades, a set of standards emerged. So buildings are controlled in a very tight temperature window. Now, so many of you probably have the experience of buildings running like this. They run at exactly the same temperature in the winter versus the summer. If we could run the buildings slightly hotter in the summer and cooler in the winter, then we can save a lot of energy. So showing this diagram is some simulation done at Berkeley. If we can expand the window by about a little bit over 2 degrees C or 4 degrees Fahrenheit, we can save 2% of US energy use, about 2 quad. So that we can, now, of course, the next question you will ask is, that defeats the point of having air conditioning because we try to keep everybody comfortable. So what do? Is that we need to develop a set of solutions that we can compensate for this wide temperature range. Basically, we try to build a thermal envelope around the human body. How do we do that? We are very technology agnostic when we started out. So we set up the program intentionally to be very broad. If you look at these different categories, they practically contains everything under the sun that can get the job done. So we're looking at delivering energy from a distance to a near range to what you wear, or any combination of the three. However, the system has to get the job done, meaning we have a set of program metrics you have to meet. You have to save the energy. The economics has to work. And I will touch it briefly later. Whatever you develop, we need to find a path to the marketplace. So with that in mind, we built up this really exciting portfolio of projects we have just announced a few weeks ago. I want to mention that one particularly exciting aspect of doing this program is that we engaged a really diverse set of people to tackle this issue, including many people who would not traditionally work on an energy problem. These people include the traditional energy experts like building experts, thermal transport experts, but also textile people and experts in studying consumer adoption of products. So these are very important aspects of energy product, but this program really gives these people an opportunity to participate. So we are supporting a wide range of ideas in this program, from delivering heating and cooling from a distance, which is more along the line of you would install in some part of the building, to solutions that's more suitable for an office environment. So I want to highlight this project we're funding at Syracuse. Essentially what they're trying to do is to make a desktop air conditioner. So it's envisioned to be the size of a old PC that will deliver chilled air to a stationary building occupant without releasing hot exhaust while it's operating. Now you wonder, that doesn't sound following the second law of thermodynamics. But the secret is really to create a time shift of this heat release. Because the delivery of the thermal energy is so close to the occupant, the actual amount of energy you need is so small. Correspondingly, the amount of waste heat you need to release is also very, very small. We are supporting a lot of wearable technologies. Some of the more interesting ones are actually relate to what Howard touched upon, even though it's for a slightly different reason. We're trying to deliver technologies with tunable insulation values, either by manipulating radiation or conduction or convection. That really round up the entire portfolio. We're really excited about the program. And in the next few years,
I don't see if I can get under. Okay, my name is Jonathan Burbaum. I'm a program director at ARPA-E. I've been with ARPA-E for 4.5 years, so I'm certainly a veteran. In that time, I've had the opportunity to read thousands of concept papers and hundreds of full applications, and all on the theme of energy. And I've just launched a new solicitation called Transnet, and Transnet is broadly in the area of improving the efficiency of personal transportation. And I want to sort of parse that for a moment, because efficiency improvement, like cost reduction in energy proposals, is mom and apple pie. You either improve efficiency or reduce costs. That's part of the game. But personal transportation, I think, is going to be a little bit different for you. We're talking about individuals moving from one place to another. Every one of us in this room use personal transportation to get to this location in some form or another, and I bet we could all figure out a way that we could have done it more energy efficiently, and that's what this is all about. In the course of analyzing these applications, I came up with these frequently assumed fallacies. Myth one is that improved efficiency leads to lower energy use. Certainly, in retrospect, if you'd used a more efficient way to get here, you would have used less energy. But the point is that there's a human involved. There's a human factor in everything that we do in energy. And in this case, improved efficiency sometimes does not lead to lower energy use. And this has actually been understood for 150 years. This is Jevons paradox, where it's the economy of use that leads to more consumption, not less. So we've got frequently assumed fallacy number one. Second thing that people sometimes say is that if all things are equal, people will choose the cheapest option. Those of you who have taken economics, this is sort of a fundamental tenet of economics. However, I posit to you that that's not true, okay? And I've chosen a cartoon to illustrate what I mean. In the left panel, you see a gentleman who's just walked in, bought a $3 latte, and asks, is there free electricity? Oh yeah, there's free electricity. Just find an outlet. You've just paid $3 for a coffee. We can give you free electricity. If he was purely going to choose the cheapest option, what he would do is he'd go home, get an extension cord, and run it next door. Because he's just paid $3 for a latte, he's just paid for his electric bill for the rest of the month. So this does not happen. People don't behave this way. And again, it's the human option that comes to the fore here. So let's see, does Jevons hold in personal transportation? I think we'd all agree that over the last 50 years, personal transportation, in terms of energy efficiency, has improved significantly. So this is a plot from 1960 to 2010 of the gallons per vehicle year. And what Jevons would say is that should be pretty much a flat line, maybe even going up, because we've improved the efficiency. What engineers would say is, well, it should have gone down dramatically. What actually happened was as follows. What you see in this graph is gallons per vehicle year. The vertical gray lines are recessions, and there are some things that happened that caused dramatic drops in the use of energy in personal transportation. One was the Arab oil embargo in 1973, the Iranian Revolution in 1979. These both led to policy impacts. In 1975, CAFE standards were passed, so now we know what the efficiency of the fleet should be. CAFE standards are implemented 10 years later. We can now calculate what it should have looked like. And it should have looked like this, okay, if everything had remained the same. I'd argue that what we've got are a combination of human factors and policy and economic factors that come together to define the efficiency of energy use efficiency of personal transportation. We need to take a look at the human factors. Now, that's what Transnet is trying to do. Transnet focuses on the traveler. And what I want to point out here is this is a graph of the amount of energy used per year on the left axis. On the right axis is the miles per gallon equivalent per traveler. Now, we've normalized the number of travelers in a particular mode, and we've arranged it in terms of increasing efficiency. And what you see here is pretty dramatic. You see that the personal transportation that we use, cars and trucks, use most of the energy, but they're the least efficient forms of transportation. If we could either increase the occupancy of those or move to more efficient forms of transportation, we could improve the energy landscape. One thing I want to point out here also is where the rubber meets the road, right? This is sort of an engineering offshoot here, but the point is that all forms of road transportation are less efficient. So if you could figure out a way to improve the rolling friction on pavement, you might be able to improve this situation dramatically by reducing the energy cost of personal transportation. Think about it. So we've got approaches to improved efficiency. I want to emphasize that all of these things really rely on the human factor. So the approaches to improved efficiency are human, economic, and technology. And I want you to think about ways that you can incorporate the human elements of technology development and deployment into these the proposals that come in for Open 2015. And with that, I guess I finished on time. Okay.
Thank you, Jonathan. I'm Mike Kane. I'm a fellow at ARPA-E, where the fellows work to identify new investment opportunities for ARPA-E. I'm here to present to you some of my work on a new opportunity for big data to realize big energy savings through automatic decision making. So automatic control has been used for a long time to drive energy efficiency. For example, think of an engine control unit. You design it once to save energy in miles per gallon in your car, and you can deploy that one engine control unit on 250,000 cars. Think about now first cost-sensitive energy infrastructure, for example, buildings, where costs of deployment and design may no longer make energy efficiency controllers economical. So let's take a look at the example here where we have a building. We have to design where our sensors and actuators are going to go and how those connect to our control system. In our control system, we have some sort of optimization algorithm, which nowadays often talks to some sort of system model. Now, designing where those sensors and actuators go and creating a model of your physical system can be a costly endeavor just because of the labor cost of someone coming out and doing that task. The question is, can we use live data streams from maybe thousands of other buildings that already have control systems in them to automate the design and deployment of new control systems? So if we look at the cost per square feet in deploying a building energy management system and compare that to building size, where if you're not familiar, 5,000 square feet is a fast food restaurant, 50,000 square feet is the size of a football field. The Gaylord has 500,000 square feet of meeting space. The cost curve would look something like this, where for really small buildings, we have low-cost programmable or smart thermostats. As buildings get bigger, they get more complex. We have multiple zones, multiple pieces of equipment that need to coordinate. In order to do that, the way that's often done is you bring someone to your site, they model your building, design a controller, then tune it on site. That's actually a relatively fixed cost of coming out and doing that. And you can spread that fixed cost over the area as your building gets larger and larger. Once you get to very large buildings, you have a high energy bill, you have low cost per square feet for deploying a building energy management system. We can now have an energy efficient and economical building energy management system. So on the market now, we see smart thermostats for homes. We see economical building energy management systems for very large buildings. But the question is, can we use data-driven modeling to help drive down the cost for these mid-sized buildings? So if we look at how much energy is used in the US in HVAC and commercial buildings, we classify buildings from 5 to 50,000 square feet. Public buildings, office, and retail consume the most, followed by other buildings, medical, and food. Those last three categories kind of have their own unique aspects to their HVAC system, so we'll focus on the first three. And we're looking at almost 1% of US energy consumption. Only 6% of these buildings have building energy management systems. Compare that to 50% of buildings that are over 500,000 square feet have them. So there's an opportunity here to deploy building energy management systems here. If we add in multifamily residential, we're looking at almost 1.5 quad of HVAC, which is $50 billion. Laboratory research has indicated that between 10 and 60% energy savings are possible. So where can ARPA-E work in this space? Algorithms and architecture for spreading the data and the computation associated with modeling these complex systems is needed, and also ways to validate these models and controllers. With cutting-edge algorithms, we need validation tools for realistic big data sets. The current approach of spending $1 million a team to generate realistic data sets isn't scalable to the future. Whenever we're collecting personal information, privacy now becomes an issue. There's new approaches that can be explored for actually calculating the risk of privacy and engineering ways that we can mitigate that both in the cyber system and in the physical system. And then lastly, there's opportunities for new technology to enable new commercialization strategies. Can we guarantee payback period using historic data, or even enable new models such as automation as a service? These research developments wouldn't just be applicable to buildings. There's 3,000 electric utilities in the US. They're all very similar, but they're all a little different. Distributed energy resources are necessitating a need to model these 50-year-old systems. Autonomous cars need models of their environment for GPS-denied areas. And those models need to be periodically updated to ensure safety. Non-intrusive electrical load monitoring requires characterizing based off of known models. As Jonathan said, the transportation models can be used for kind of energy-aware routing. If we learn something in one city, can it be applied to the next? And we have 13,000 chemical processing plants in the US. Can we apply some of this technology to that? So in summary, can we collect big data from distributed mid-sized energy infrastructure and apply that to automate design and deployment of energy-efficient controls? So I'm pretty excited to be working in this area at ARPA-E. I can't do it without your help and your proposals, though. So feel free to reach out to me at my email address here, or come meet me afterwards at the summit. Next, Eric Schiff will.
Thank you. The simplest but least efficient window is just a single pane that separates you on the inside of a building with the cold world outside. At ARPA-E, we've been considering a research program that would attempt to transform these single pane windows into high-performance ones. Well, what's wrong with single pane windows to begin with? Of course, they're inefficient, about 2 to 4 times less efficient as far as heat flow goes than a modern double pane or insulated glazing unit. That's one reason. Another reason is comfort. You can see here a picture of my colleague sitting in her parka near a single pane window in winter. If you have single pane windows in a cold climate, you lose floor space near the windows that's unusable to you. But perhaps the worst of all is that single pane windows are the enemies of a healthful indoor humidity. If you've attempted to raise the humidity in a house with single pane windows, for example, if you have a sick child, you'll discover it's practically impossible because of condensation problems. So in any case, those are some of the difficulties. Speaking of children, perhaps you remember the story of the ugly duckling who's expelled by the older ducks in a flock. I like to say that single pane windows are the inefficient ugly ducklings of the building envelope. But that very inefficiency creates an interesting opportunity. Single pane windows are not the majority of windows anymore, but they are the majority of heat users. About $20 billion a year is spent to drive heat through single pane windows to keep houses warm. That's more than is used by all the other windows combined. The opportunity it creates is that very inefficiency creates money that you can use to try to upgrade the system. There are about 15 billion square feet of these windows left, or a retrofit market that is feasible if we can only develop products that work, of about $150 billion. The simplest solution would be just to replace single pane windows with modern IGUs, that's insulated glass units. They're the sealed up type. Anyway, they last between 15 and 30 years, depending on which manufacturer, which means that the rate of return just from energy savings is actually less than 0. So you can't make an economic case. However, many building owners do want to upgrade for some of the reasons I'd already mentioned, such as indoor air quality. But even here, there are some interesting opportunities for new technologies with buildings that cannot be upgraded with IGUs. For example, historical or architecturally significant buildings. And also certain mid-century skyscrapers. Here's a picture of one that was never designed to take all that weight in the glass. There's so much glass weight that if you double it, the building simply is unstable. So you can't use double pane windows or insulated glass units there. So when ARPA-E considers a new research program, we hold a workshop, and we did have one in November. The workshop record's posted on the web if you're interested. There are a lot of technology options that exist that could be applied to this problem. So I like to sort of show it with spray paint cans, but there's many ways to apply it. That's just a kind of a joke. First of all, super low emissivity, right? Windows have very high 90% emissivities. That's bad. That's inefficient. You'd like to drive that down to about 10%, and there are already products, window film products, manufactured in the US that can do that for you. So there's one piece. I just discovered a Japanese product which actually is a spray paint. You spray on conducting oxide particles, and you achieve the same effect of a nice, low, efficient emissivity. But that's only part of the picture if you drill down into it. There are other qualities that you need to get a good window. So in addition to the emissivity, one could use, it would be very helpful to have a thin layer of super insulation. And people have been trying to do that for many years. Probably the best known technology for that is silica aerogels, which are actually used in skylights today. Anyway, that's an excellent approach. It has some problems with application and clarity, and so one wants to look at all the options. Another cool approach is to make little silica nanoshells, which can be piled up as an aggregate and also have excellently low thermal conductivity. Still another one, you can use block copolymers to template three-dimensional networks of silica that have many of the good properties of the nanoshells or the aerogels, but it's an orderly lattice. This helps you control transparency in a new way. Still another option, nanofoams. There are many, many options that you can consider applying. So I'll conclude by saying that we are considering the possibility of offering a research program in this area. I hope you will email me or find me around the meeting if you have suggestions for how we should organize that. And let's remember the goal. In the children's story, you may remember what happened to the ugly duckling. The inefficient single-pane ugly duckling, of course, grew up into the swan of the building envelope. Thank you.
Okay. The technology is working, and so you are welcome, if you haven't already, to text in questions. We have a few here, and I guess I'll turn first to Ping Lu. Ping, do you see lighting playing a part in the goals of Delta? Lighting.
Lighting?
Lighting technique, yes. I guess I would interpret that as personal lighting rather than lighting the entire space.
That's certainly, you know, it's outside of I mean, the focus of Delta is really to look at the sort of amount lighting and thermal management. Because of diffusive nature of thermal energy, it's the sort of arguably the most difficult technically to do. I mean, obviously, to localize the heating and the cooling is not new. What's new is whether today, with today's material sciences and the photonics, these advances, whether we have the opportunity to actually make technologies work. I would say lighting, if I interpret a question as whether localized lighting can be more directional localized lighting, I think that's already happening. So definitely will make a difference.
And for Eric Schiff, Eric, if such a good window can be made with a single pane of glass, why haven't the big window manufacturers done it yet?
Well, the truth is the technologies for this either don't exist already or are not ready for commercialization. Single pane windows with low emissivities built in are well known. It's called hard coat. So that does exist, and that's a good thing to do. The window films are actually more recent than the hard coats single pane windows and actually have lower emissivities than the hard coats. So that's relatively recent. I believe 3M has just started marketing them in the US. There's a couple of other companies, Eastman Chemical and SolarGuard, which is Saint-Gobain. Anyway, all of these companies market in the US. There are other companies that market overseas. But those are only partial solutions. They don't attack the condensation problem of single pane windows. So for that, we'll actually need to make some of these thermal layers or some other equivalent technology succeed. That technology really is not really ready for prime time today.
Thanks. I think this one's probably shared between Mike and Jonathan. Is big data applicable to the personal transportation problem?
Well, I think it is. It's a big data problem with big privacy issues. So I think that a pure big data approach to personal transportation probably is too big. You have to be selective about the data that you pick for that approach. But Mike, do you?
Yeah, it's a big data problem, but it doesn't have to be a big data everything in one spot. If we can compute the little bits of data and just send appropriate information up from each individual node that might be streaming information to its local computer and passing it up, then we get around privacy issues and we get around bandwidth issues of the wireless communications that are likely being used. So, depending on how you look at it, yeah.
Thanks. Ping, can you comment on required market adoption rates and cost targets for your program? It sounds like interesting technology. I guess the question is really about adoption rates and cost targets.
Sure. So, we, as I mentioned, when we were developing the program, we are very mindful of the adoption side. And as a matter of fact, that's one aspect we were particularly excited about because in some of the more closer to the consumer technology side, unlike you work on car engine, because most of the drivers don't really see or need to know how the engine operates. But in this particular case, consumers will have direct interaction with whatever we develop. So to make technologies that will be convincing enough for adoption is a critical piece. That's why we engaged the academic and the industrial communities who actually study these as a profession. So it's something we don't do as much in the energy space because a lot of the time we're developing enabling components for a big system. So we're very mindful of that. On the cost target, I want to mention that like every ARPA-E program for every energy product, we're very mindful of cost implications of these new technologies. So one angle we looked at is if you look at the census data, we actually looked up about the annual household purchase of, say, personal apparel versus household annual energy bill. Like that can be deconvoluted into the expense for heating and cooling. They are actually a lot closer than you think. They're really on the same order of magnitude. So energy saving, if these technologies can achieve energy savings, then we set the 3-year payback period, which is a sort of a dream goal for a lot of building-related technologies. That's what drove that. And we did a fair amount of analysis. We think ranging from desktop solutions to wearable technologies, I think we do see a variety of paths to get there.
So probably a similar question for me about the GTI project. In fact, we have a number of projects like that that are trying to develop a new hybrid solar collector, hybrid solar converter that produces both electricity and stored heat at high temperature for dispatchability. The question is, what's the path to market for these solutions? How big is the market? It's difficult to see how this is broadly adopted. So what we do know today is that thermal storage by itself is much cheaper than electrical storage. comparing electricity in to electricity out, it costs you a lot more per kilowatt hour than it costs for thermal storage, where you put heat in and get electricity out. The problem is the cost of collecting that solar heat is very high in concentrated solar thermal. So the idea of that project and the others in focus is to lower the cost of collecting that heat and generating that after-hours dispatchability. Now, what's the path to market? Well, it may be, in some cases, there's a secondary stream of heat coming off of these systems that can be diverted to industrial use. It may be that you don't even start with dispatchable electricity. You start with some electricity that can be sold into electricity markets, and some heat that can be used locally in a process facility. That's one of the reasons I chose, out of all the projects, that GTI project, because their new thermal fluid isn't flammable. So you can imagine putting it right next door to an industrial facility. Look, concentrating solar power hasn't caught on right now because the scale of investment is about $500 million to put a new plant in. It's just too large. So the idea of these systems is, by lowering the cost, people can put them in more modular forms and get over the barrier to investment, and we can have more than the 20 cycles of learning we've had in concentrating solar power. Let's see. Jonathan, how far can you reduce wheel-to-road friction before it becomes dangerous in terms of stopping or controlling the vehicle?
You know, this actually came to me as I was developing the slides for this. I think that the challenge there is to sort of, if you can develop a directional friction, so you sort of claw the road going forward, are able to roll forward easily. I'm sort of throwing it out to the innovation of the audience to come up with ways of doing that, because I looked at the rubber to pavement friction compared to rail on rail friction. It's about a factor of 100. So, you know, you can travel further by rail on fuel because of that rolling friction. I think it's an interesting problem that I'm just going to sort of throw it out there for the creativity of the audience to come up with potential solutions in that.
Yeah. Another one for me, 8 Fahrenheit of free cooling sounds too good to be true. Are there any limitations on that approach? Of course, I didn't say it was free. I said there were no energy inputs. You still have to manufacture it, and it will actually have to be quite a lot cheaper than photovoltaics to play an important role on a square meter basis, because cooling doesn't have as much value as electricity, and you know, you can produce cooling with a high coefficient of performance, and so cost is going to be everything. And it's not free. It's only the added costs after you install it that are free. Ping, can you comment on the possibility of thermoelectrics being used as wearable devices? Can thermoelectrics be used as wearable devices? What are the challenges?
Yeah, so actually in the portfolio, we do have we have funded the work related to thermoelectrics. But the challenges for using, among all the cooling technologies we have looked at, you know, thermoelectric probably is the best known, but it's also, it has tremendous challenges. If it's for wearable, it needs to be flexible in some way, and the coefficient of performance has to be high, because since it's an active solution, it requires a power source. And I can tell you, I studied battery for a living before I joined ARPA-E. I don't like batteries. So you know, if I don't have to use it, I try very hard not to use it, or use a very small amount of it. So those are really the challenges. However, I would say in this particular application, it is a unique opportunity for thermoelectrics. There is a plus side, because the delta T we are looking for is very small. So when the delta T is very small, the coefficients of performance tend to be very good. And there are not many applications like this for thermoelectrics. So that's why it's part of the mix.
So a few degrees will help me feel better in a hot environment.
That's all you need.
Yeah. Jonathan, how will you incentivize drivers to take more efficient routes or use public transportation?
Right, that's part of the challenge of Transnet, is developing that sort of control structure. It actually came from drawing analogies between a lot of the smart grid efforts that are going on at ARPA-E in terms of efficiently routing electricity around the grid. Could we use that same sort of mental construct to do that for people in the transportation network? And obviously electrons are easier to control than people. So I think the challenge there is really coming up with an incentive structure that is socially and technically socially acceptable and technically feasible.
This is for Mike. Mike, can you speak to where you see specific opportunities to monetize your ideas? How do people earn money from big data in energy?
So I think just the opportunity is to drive down the cost of control systems that are already proven in labs, but they require a PhD to deploy them. So if you can make those energy efficiency systems a lower capital cost or a lower first cost, then you can derive the savings from derive your profit from the energy savings. And that, like I said, might enable new approaches to commercialization, like automation as a service. Maybe you pay your hot air bill instead of your electric bill. So there might be new approaches to kind of bring those energy savings out by using the big data to drive down the cost of deployment.
And then another question for me, why don't we see more use of light piping, natural light, technology to interior spaces of buildings? You know, you get double value when you can get daylighting into the interior spaces of buildings. You avoid the cost of the lighting, and you also, at least most of the time and in big buildings, avoid the cost of the HVAC, of cooling the building to dissipate to cool the heat that's dissipated by the lighting. So the question is, why don't we have more of those? Well, at the moment, the trackers are very expensive, and we are funding a few different projects that are trying to get rid of that tracking expense. And you have to imagine being up on the roof and following the sun across the day, or else you get very few hours of lighting. I mean, also the competition from LEDs is sort of intense, although the quality of LED lighting is not as well liked by occupants as day lighting, and it may make LED lighting finally more acceptable to occupants if you can mix some day lighting in. So, interesting question. Let's see, Eric, can recycled or reclaimed materials help bring down the cost of increasing efficiency of windows? Recycled or reclaimed materials.
Recycled or reclaiming materials. Well, I don't know if I have a direct answer to that. Let me try the following. There's two ways to look at single pane windows, which is what I'm trying to think about. One is a sort of applied film that would prevent the need to break out the window and replace it. So that would be a plus for recycling. Another solution, which is used, for example, in the mid-century skyscrapers, is in fact to remove the old window where it would then have to be recycled at some cost and put in a new single pane that matches the weight requirement but has better properties. Other than that, I'm not sure I see the direct connection between recycling and the single pane project.
Mike, what will the role of large building management companies be in next generation data analytics? Will there be new players? I guess the question is, or will it continue just to be the Honeywells and Siemens of the world?
Yeah, so by having a leg up in large buildings already, building energy management systems like, the Siemens and Honeywells of the world definitely have a leg up, but they're not in this mid-sized building space necessarily. Maybe they are for big box stores where they're 20,000 square feet and they have 1,000 stores, and you have one owner trying to drive down the energy of all of these buildings that are exactly the same. But when all of the buildings aren't exactly the same, there could be opportunities for new players. It's definitely going to be a hard space because you don't have the data until you're in 3,000 buildings, and you need 3,000 buildings in order to generate the data. So that's where the opportunity for synthetic big data sets becomes interesting.
I guess this one's for Eric again. how do you address the installation cost for single-pane window retrofits?
So if you're trying to drive the retrofit solely from the energy savings, essentially you're limited to a price of the product of about $10 per square foot to get a reasonable payback period. It varies according to the climate you're in. Clearly the payback period is shorter in the north than it is in the south. So in any case, you definitely have to include the price of the product in your technology development. So expensive products won't sell.
And I think unfortunately, we have a couple of questions left, but I will just wrap up with one last question for Ping Lu that's probably the right one now. If your program Delta has already been funded, can someone get a new idea into it? Because that's applicable really to all the ARPA-E programs that have already been funded. Is there some way to get in after the money's gone out?
Sure. So as many of you know, and we mentioned this a couple of times, that we do have the Open 2015 call on the street right now, and you still have time to submit whatever energy-related idea and to cover any of the topics we talked about today and then beyond, because that's an all-encompassing FOA. In addition to that, we also have a ideas FOA, which is more a seedling type of program that is open. I think it's reissued for another year to the end of September. And in that case, if you have a particular idea, proof of concept idea, you are encouraged to apply. And you also have the option of contacting one of the program directors so that you can get some initial feedback on your idea. Unlike the 2015, which is the only way you can communicate with us is through the website, I believe, the ideas FOA does allow open communication with people at the agency.
So with that caveat about the Open 2015 FOA that we can't talk to you, speaking for everybody here, we're glad to hear your ideas in energy, and hopefully they will help us determine what the next great ARPA-E program should be. So thanks a lot for your attention, and I think it's break time. Thanks.